What I'm going to talk about is more generically about turbulence, and it'll be very focused on the IMF and on what this means for star formation. But I hope to talk to you about why really a very basic set of processes involving turbulence and gravity governs a much broader aspect of the physics in galaxy formation and in astronomy as a whole, and links many of the phenomena on small scales and large scales, which is really, where the cutting edge in a lot of galaxy and star formation is linking these small and large scales together. So I think that's particularly important to push on. So of course, turbulence we all know and hate. It's important on essentially every scale in the ISM and arguably a lot of scales in the IGM, and it's a mess, right? We simulate it because it's hard to do, and especially in the ISM, essentially every bit of physics you can think of is important at some point or another, which again makes it's a very rich field. It means you can work on all sorts of physics depending on what you find interesting, but it also means it's kind of a nightmare. And if you wanted to have a complete simulation that really captured all the physics, good luck. We're definitely a long way away from there. So with all of this, how can we make progress? It seems like this is this wildly nonlinear, chaotic problem with, incredibly sensitive to initial conditions, et cetera. But yet, as I'm sure has already been discussed, what's very striking is for all this chaos, there are these really remarkable regularities in the structure of the ISM in galaxies and in star formation. And these are just a couple of examples. I could show you dozens of correlations that would make this point, but I just want to highlight a couple. And on the left is the stellar initial mass function. So this is the mass function of stars at the time they form, right? And this is just number as a function of mass. And this is from a compilation by Nate Bastian, but there's many others. And the point he and many, many other people have made is over a huge range of environments, this is essentially a universal function. And the shape of that function, pretty roughly, is a power law at high masses with a slope that's close to -2, where the slope that I'll refer to being close to -2 is the number dn by dm proportional to m to the -2. And -2 is an interesting number that I'm going to repeatedly come back to in this talk, because if this number were exactly -2, it would mean that there's equal mass per logarithmic interval in mass. So -2 is a special number because -2 is where things are really, truly self-similar across scales. They're really scale-free. And so it's close, but a little steeper than that. And then there's this sort of log normal-ish rollover at low masses. And then on the right, what I'm plotting is the mass function of giant molecular clouds from a compilation in Blitz and Rosolowski. And what you can see, they've rescaled the normalization of these axes. But otherwise, these are so it's just comparing the shape here, but of mass functions of GMCs observed in a number of nearby galaxies, as well as the Milky Way. What you can see is the shapes are nearly identical. It's pretty obvious right there. And they have a power law slope at low masses here that's, again, very close to a -2 slope, a little shallower in this case, and then some exponential-ish cutoff. So it's pretty remarkable that there's this degree of regularity and maybe even this similarity in the power law scalings here. But what's really crazy is, let's plot one more mass function here. That's the mass function of dark matter halos. And that is not an exaggeration, that is not made up, that is actually, the line there is made up, okay, fine. But if you plot the real mass function of dark matter halos out of your cosmological simulation, and you rescale the normalization by a much bigger factor than the GMCs in nearby galaxies, it lies right on top of this. Same exponential cutoff, same slightly shallower than -2 slope. So what is going on here? Well, this similarity motivates a lot of what I'm going to dive into. But at a very basic level, this should push you to think, okay, what could these systems possibly have in common? Well, there's basically only two things that I can think of that dark matter halos have in common with giant molecular clouds. Gravity, which is the same, and some kind of random field, which I'll explain in just a second. So what do I mean by random field, and how could this dark matter halo mass function provide us some insight into what's happening in the turbulent ISM and inside of molecular clouds? Well, we actually have a very good analytic model for why the mass function of dark matter halos looks like it does. That's been well tested and incredibly well understood. You can literally find hundreds of papers on the archive that work this out in varying degrees of detail. The basic methodology goes back to Press and Schechter. And so how can you calculate the mass function of dark matter halos? Well, you can just brute force it. You start with your cosmological simulation, seed it with initial conditions that look like the statistics of the universe at recombination, where we observe the CMB, and then just evolve it forward following gravity. Or you can use this analytic method. And the basic idea of Press and Schechter's approach, which you'll also hear called the extended Press-Schechter approach or the excursion set formalism, they're really all the same thing, is that you start with this random field of small fluctuations. And the initial fluctuations in cosmology are a Gaussian random field. And in cosmology, they happen to be a nearly perfect Gaussian random field. And they have a well-defined power spectrum. So you know the power spectrum of those fluctuations. And that's useful because the power spectrum essentially tells you what the variance in those density fluctuations is. It tells you that if you plunk random spheres down of a given size on the initial matter field, what's going to be the variance in the density that you measure in those spheres. So you can estimate what that variance is. And then you can also do a very simple calculation that says if the density in this initial sphere is bigger than some critical value, then by today it will have had strong enough gravity that it'll detach from the Hubble flow, turn around, and collapse. Right? It's basically going to be sub-escape velocity in the Hubble flow, and it's going to turn around and collapse. You can work out what that critical density is, and it turns out for cosmology it's a really simple number. It's basically 1.8 times the mean density is the critical density where you'll turn around and collapse. And then this entire mathematical architecture that people refer to from this methodology, which can get pretty messy, is really just, it's messy, but it's really just a way of counting. It's just a way of doing the statistics correctly to essentially count the number of regions or count the mass that is above this critical threshold and is going to detach. And so you just use basic statistical properties of random fields to count the mass that's above that. And I'll explain a little more what I mean by count in a minute. And that gives you an analytic mass function that in cosmology is very well tested. So how do we make the analogy from this to what's happening in the ISM? Well, the ISM is not seeded by inflation, the density fluctuations in the ISM. However, a lot of what's happening in the ISM is being driven by turbulence. And there are some very basic expectations we have for what turbulence does. So first of all, turbulence obeys a well-defined power spectrum, and our understanding of this goes way back. You can think of it in many ways. This is just one way of writing it. So the energy, which you can think of as the velocity dispersion of the turbulence averaged on a given scale. K is just 1 over the scale that you're averaging on. That's just the way to think of it. If I average on a given scale 1 over K, then the energy or the velocity dispersion on that K, so this U squared is just velocity dispersion that I would measure, scales as a power law in K, where P is a number between 5/3 and 2. And there's, again, hundreds of papers on where between 5/3 and 2 it lies, depending on the details. But for our purposes, we don't really care. Or at least for purposes of this talk, I don't really care. There's a lot of interesting physics inside that distinction. But we have a pretty well-determined idea of how the velocities scale. And you measure the velocity in a given scale. It just scales. The RMS of that scales like a power law. And we also have a pretty good idea of what that means for the density statistics. There's been an enormous amount of work, particularly from the astrophysics side, on studying what that means for density fluctuations. So you have this fluctuating velocity field. Flows converge and diverge, and as a result, they drive density fluctuations. And it's very well established that at least if the gas is isothermal, and I'll mention a little later what happens in other cases, but all the intuition that's relevant for this comes from the isothermal case, you get a log normal density distribution. And that's what's plotted here. This is measured in different simulations. And the reason for that's very simple. I meant to have this equation in the slide, but basically, if you take just isothermal gas and you don't have any molecular viscosity or any external forces, the continuity equation is very simple. You can just write it as the derivative of log rho by dt is equal to grad dot v, or minus grad dot v. So what this means is that when you have a compression or an expansion in the gas, you multiply the density by some number. And that number is just this sort of random fluctuating velocity. Well, so what happens if you continuously multiply a field by random values? Central limit theorem says you get a log normal distribution. You get a Gaussian distribution in the log of the variable rather than the linear field. And that's all this is. It's just central limit theorem. And furthermore, the simulations have given us another major insight, which is how if it's a Gaussian, there's only really one parameter that fully describes it, which is the variance or the dispersion of the Gaussian. And we can measure and fairly simply analytically understand how that scales. And this is just one example from work that Jim was a part of, but he's looked at this quite a lot in detail and can tell you about all the subtle ways that I'm glossing over details here. And, but basically, the variance scales as the log, because we're talking about log density, of the Mach number squared. And again, it's easy to see why that is. So that basically, this is just saying that the RMS fluctuation scales as the Mach number, which shouldn't be surprising from this, right? The characteristic logarithmic fluctuation is proportional to the velocity, right? And the Mach number is just velocity divided by sound speed, okay? So it has to basically be proportional to the Mach number. This is really the only scaling that physically could come out. And alpha is just some ordered unity constant that, again, a lot of simulation work has gone into figuring out. But that's basically the key scaling. So that's very simple, and we think we understand that. And that gives us a way to say from turbulence, if we know that there's turbulence there, we can basically predict what the density field's statistics are going to look like, driven by turbulence. So what's the next thing we need if we want to make the analogy to cosmology complete? Well, we need to define some critical density that's interesting, where gravity is going to win, right? And that will form objects that we think are interesting. Maybe our definition of interesting objects has nothing to do with gravity. You could, in principle, do this problem for totally different questions like that. But for star formation, we're going to assume that stars form out of something that at some point is self-gravitating. And I don't think that's a crazy assumption. So you can write down in an ISM what the dispersion relation is, and I forgive me for putting a giant equation up. But basically, this is just asking if I have a density perturbation, you can write down a dispersion relation for it. Basically, this is the frequency of the perturbation. The important thing to know is if this right-hand side is negative, then you're unstable. The perturbation grows exponentially, i.e., you're self-gravitating and you collapse. If the right-hand side of this is positive, then it's a stable perturbation, and we don't care for purposes of star formation. So this is a big expression, but I just want to list what the terms are so you have some idea of what the major competing forces here are. So this first term, kappa squared, that's the epicyclic frequency. Basically, it's the orbital frequency in a disk. And all this term represents is angular momentum. It's the circular velocity divided by the radius you are out in a disk. And it's just the fact that angular momentum resists collapse. Okay, so you have to overcome, and that's positive, right? So if we want gravity to win, we have to overcome angular momentum. Next, we've got cs squared, which is the sound speed squared. So that's essentially the temperature of the gas. And this K, again, is just a scale term. And this is the thermal pressure. So, of course, you have to overcome thermal pressure if you want to be self-gravitating. And that, because remember, K is sort of 1 over scale. This term goes as r to the minus 2, which means it dominates on small scales. Again, intuitively, you can think of it on large scales, the sort of global dynamics of the disk. The angular momentum dominates. On small scales, pressure dominates. There's kinetic energy in the turbulence itself too. So if we want to say your collapsing potential outweighs kinetic energy, you need to count the energy in turbulence, and that's all this is. It's just the turbulent velocity dispersion. And because that's some power law, what you get is that this dominates in between these two. So it dominates on intermediate scales. There's some scale called the sonic length that I'll come back to being important, which is basically the scale where the turbulence is weaker than thermal pressure. Because for any realistic turbulent model, basically most of the energy in turbulence is on large scales. And as you get to smaller and smaller averaging scales, turbulence gets less and less important. And then finally on the far right we have gravity, and the expression's a little messy, which you don't need to care about these k's and h's. The important thing is it's got a g because it's gravity and a rho because it scales with the density. So if the right-hand side, if this term is bigger than these terms, you collapse. You're negative in this equation, you collapse. And you can rewrite that as some messy equation that defines this critical density where you'll collapse under gravity. And this is, as you can tell, much messier than the cosmological case where this was, a number. But it's still some, you can just plug in the values that you care about here and say whether or not what the density that you'd need to be above would be. So that basically defines our analogy to the cosmological case. So I'll spare you the actual detailed math, but I want to illustrate how you go about this counting exercise then. So what do I mean when I say we count the regions that are interesting, and why is that? Why does the counting actually have information in it? Which it sounds really boring when I call it a counting exercise, but you get a lot of important, I think, physical insights out of this. So what I'm showing here is a random realization of the density field. And what I mean by that is that knowing this power spectrum of turbulent fluctuations, I can essentially take a random realization of that power spectrum. I'm essentially picking a random point in space and saying, I assume that this randomly samples the power spectrum. And I just have some Monte Carlo realization of that. And what that physically turns into is the density averaged in spheres about a given point with successive sizes. So this averaging scale R, I start on, say, size 0, and I average up and up and up into bigger and bigger spheres, integrating, just this power spectrum. And of course, this is the density relative to mean, so on sufficiently large scales, it has to be the mean density, because now I'm integrating over the whole galaxy. I can't, mass conservation means that has to go to the mean. On small scales, it can have various, whatever value the local density has. So this is just one random point in space where I've just essentially done this Monte Carlo experiment. Other points in space might look very different. They might fluctuate differently. They might go down here. They might go across here. They can do all sorts of things. But I have this one random point, and now I can compare it to that complicated expression that I showed earlier for what the critical density above which gravity wins is. And that's what this red line is. So above the red line, gravity wins. All right? And again, it's not a constant. It has some funky shape. But qualitatively, the important thing is that on very large scales, angular momentum prevents collapse and makes this harder. So it starts rising here. On intermediate scales, turbulence dominates. And on very small scales, thermal and magnetic pressure dominate. All right? And that's basically the threshold that any random point in space would have to broach to be self-gravitating. Now what's interesting about this particular random realization, the truth is most random realizations, remembering that these are just random points in space, most random points in space for a reasonable set of parameters are not going to cross this line. A random point in space in the Milky Way is not likely to be self-gravitating, right? But I chose this line because it is interesting because it goes above this red line. And in fact, you can see it goes above it at various points. So the largest scale that it goes above it is right here on maybe 50 kiloparsec scales. So it's self-gravitating on 50 kiloparsec scales. That corresponds to some very large structure order of the disk scale height, like a GMC, right?
50 parsecs?
Oh, sorry, did I say 50 kiloparsecs? Yes, that would be crazy. Sorry, 50 parsecs. My last couple talks have been galaxy cosmology centric, so my mental scales are all wrong. Thank you. And everybody feel free to interrupt at any point. If I'm throwing out terminology you're not familiar with, or if I'm doing something stupid again, just let me know. All right, so you've got this big 50 parsec scale thing it's self-gravitating all the way out to 50 parsecs. So that's a pretty big object. That's like a giant molecular cloud. But what's interesting is you see this crosses several times on smaller scales, which means that it's not just that the whole 50 parsec blob is self-gravitating. It means that on some smaller scale, here 10 parsecs, here 1 parsec, within the blob I've got a subregion that is in and of itself self-gravitating. So there's little subregions inside the cloud on various scales that are independently self-gravitating. And because the absolute value of the densities are higher here than here, they're going to collapse faster than the parent cloud collapses, right? So essentially this very dry Monte Carlo line that I've drawn here is the analytic representation of this turbulent fragmentation of a big parent cloud. It's got many subscales that are independently collapsing on their own dynamical times. And we've essentially just made a prediction for what one cloud might look like and what subscales in that cloud would fragment. It looks better when you show the movie. So I'm going to use a couple terms for the rest of the talk just to define what I mean. First crossing, it's a term borrowed from cosmology and terribly boring. All it means is the largest scale that this crosses the line, that it becomes self-gravitating, if there is such a scale. So the biggest size scale in which you're self-gravitating at a random point. And that physically, for something like a galaxy disk, which this is sampling a random point in, corresponds to something like a giant molecular cloud, the biggest self-gravitating structures. But then there's also a small scale, the last crossing scale. And this has no analogy in cosmology. This is unique to the ISM because gas can dissipate. In cosmology, you don't care about these substructures because they can't internally collapse, basically, independent of the big thing. But here they can. So there's a smallest scale, last crossing, that you're self-gravitating on. And what's important is that no subscale here is independently self-gravitating, which means that this thing's collapsing and nothing inside it is breaking off and collapsing internally separately from the little parent cloud. So that physically sounds a lot like something like a core and might be analogous to something like the core mass function or the initial mass function of stars. And you can follow this through and push the cosmology analogy even further if you want and essentially construct a whole fragmentation tree analogous to the way people do in cosmology for halo merger trees, except that the arrows run in the opposite direction here, right? You have one object that fragments into many instead of many that merge up into one. Although you can have mergers as well in this whole formulation. And remarkably, this actually agrees fairly well, at least in some of the gross properties it predicts, with the full simulation of a simple turbulent cloud and how fast it collapses and what the mass spectrum it collapses into are. But I'll show a little more comparison in a minute. So let's tie this back to reality and think about what this means for ISM structures. So if you recall, I said these first crossings, the biggest scales that are self-gravitating, are kind of order of magnitude like the scales of GMCs in the ISM. So let's see if that comparison holds any water. We can calculate what the mass spectrum, essentially we just count, we just do the simplest thing. We'll just do a Monte Carlo experiment. I'll realize 10 million of those lines. It's still a heck of a lot cheaper than a full numerical simulation. It takes me about a minute on my laptop. I ignore almost all of the important physics. But I get some set of first crossings or big structures. And the black line shows the mass spectrum of them for different galaxies, where I'm taking the global parameters of the galaxy. You need to know numbers like what's the actual mass of the galaxy to assign absolute values here. But as soon as you do that, you can do this exercise. And the orange lines and points are what's actually observed as the molecular cloud mass function in those galaxies. So it's pretty remarkable to me that with that very simple, very limited bit of physics we've explored, you're able to reproduce these shapes so well. And that comes out quite robustly. So the full, sorry, this is just meaningless the way I've written it there. Unfortunately, you can't write down a clean, closed-form analytic solution for the mass function in terms of all the general variables that I've mentioned. But if we make a couple simplifications, then you can. And those simplifications are pretty reasonable. Let's assume that we're on scales much bigger than the sonic scale, the smallest scales where turbulence dominates over thermal pressure, which for the Milky Way is something like 1/10 of a parsec. So for GMCs, we're way above that. And let's assume we're below the scale height of the disk. Okay, so we can ignore, say, global structure of the galaxy in this calculation. Then you can actually write down an analytic closed form version of what this predicts for the mass function. And that's dn by dm goes as m to some power law with an exponential cutoff. And it shouldn't surprise you that this is essentially exactly identical to the canonical Schechter function, mass function that we use for cosmology. It's a power law with an exponential cutoff. The exponential cutoff is at the global Jeans mass of the galaxy. Now that's the biggest scale on which structures really form. And that's basically what's causing these cutoffs here. And that's pretty straightforward to understand. Okay, it's hard to form things much bigger than a Jeans mass. And what's the power law? Well, you can work through what the power law should be, and you get that the power law is -2 plus some messy correction plus, I could expand this to awful high orders and nobody would care because the observations aren't good enough to measure these slopes to 1%, nor would I trust the physics in here to that level of accuracy. But the important thing is you get -2 plus a small correction. So what's happening? Remember I said -2 is this magic number that represents things that are completely scale-free, right? There's equal mass on all scales. There's equal amounts of structure on all scales, right? You can zoom into it and it looks the same. It's almost fractal. So turbulence inherently is scale-free, right? It's just a power law cascades. Gravity inherently is scale-free. It's just a power law itself. You can scale out the absolute values of everything. So in fact, -2, if all there was turbulence and gravity with infinite dynamic range, would have to be the answer. It's the only answer this system can go towards because all the physics, if all there is turbulence and gravity, they're all scale-free. Now you get this small correction because there's actual finite scales attached to the problem, like the Jeans mass. And essentially this relates to the fact that this curve here that I drew is not a straight line on this plot. It's got wiggles in here because of things like angular momentum and thermal pressure, et cetera, and those produce this small correction. And the sense of the correction is that the slope's a little bit shallower than -2, which physically means there's a little bit more mass in big things than small things. And the reason for that is just that it's harder to collapse on small scales than on big scales. Thermal pressure is a little more effective on small scales, say, at preventing collapse. Turbulence is a little less powerful on small scales. So it's easier to collapse on big scales. And that's why you get a slope that's a little shallower than -2. And that's the physics that drives this shape entirely. So let's go the opposite direction in scale and ask about cores and the IMF. So we said there's this last crossing, smallest scale, and let's see if the analogy holds, if that looks like what we observed for the IMF, for the things that are actually going to form stars. Well, so this is this calculation. The black line is this mass function of these last crossing scales, and the red line is what I had previously shown for giant molecular clouds. And here, I'm comparing the Chabrier and Krupa IMFs, where I've done the usual cheat that people who use these simple analytic models of core mass functions use, and I say, I give myself the freedom to multiply these things by a number, say 3, because there's going to be some mass loss in messy physics, like feedback between the actual core and the star. So I don't take the absolute position here very literally, because I'm probably sweeping away very important physics that I'll try and mention a little more in a minute. But the shape is the important thing to take away, how similar those are. You can zoom in detail and compare to observations. Oh, sorry. So the shape, actually, yeah. Let me explain what that shape is for a second. So I just explained or tried to give an argument for why the GMC mass function has the shape it has. So what about this? It's a pretty similar shape, actually. If you recall, this slope is close to -2. It's slightly steeper than -2 here instead of slightly shallower than -2. But the same physics means that it has to be close to -2, right? Because these are pretty close to scale-free physics. Why is it steeper than -2? Well, the simplest argument I can give you, the reason it happens here is because we're counting in the opposite direction. It's the same exact physics that make the GMC mass function slightly shallower than -2, but remember, we're counting from bottom up instead of from top down, basically. The smallest things instead of the biggest. And so basically all you do, you get the exact same, if you work it out mathematically, you get the exact same correction term, you just flip the sign. Just because it's easier to collapse on big scales, to fragment on big scales. And then what causes the turnover? Well, at some scale, however, this sonic scale, turbulence becomes less important than thermal pressure. If I average on very small scales, about 1/10 of a parsec, say, in a molecular cloud, the thermal pressure starts to become bigger than the ram pressure in turbulence. What does that mean? It doesn't mean that thermal pressure suddenly becomes much more powerful at resisting gravity, but it means that turbulence suddenly becomes much less good at producing large density fluctuations. I can no longer randomly rely on colliding flows within these very small scale regions to produce giant density fluctuations, the way they do on very large scales in the disk. And so I don't produce new structures that are even smaller and smaller. And eventually, I just wipe out all the structure, because it's all just smoothed out by thermal pressure. And I get this sort of log normal turnover. So the scale here is really this sonic scale. Basically below here, at least in these models, is where the turbulence is subsonic, right? And not able, therefore, to generate significant density fluctuations. And then you can compare this to observations of real cores instead of doing the cheat I just gave, and it's actually fairly encouraging, although you could get into a whole discussion about the definition of a core, which is a very important discussion to have, and I'd be lying if I didn't tell you I chose the optimistic, well, optimistic in the sense that they agree well with the model definitions of cores. So that's a very important but very detailed discussion to get into. You can do other things with this sort of modeling as well, and I just want to mention them very briefly. You can look at things like the correlation between sizes and masses of self-gravitating objects, sort of Larsens laws, like the line with size and size-mass relations of collapsing regions in the ISM, and those fall out fairly naturally from this. I mean, essentially, we've already calculated that in what we've described, right? We had to have a size and a density for every object, so, and a velocity dispersion of turbulence. So we know these numbers already. And they basically fall out fairly naturally. You could even, again, pushing the analogy to cosmology, this doesn't just contain information on the number of objects, it contains information on their spatial correlations with each other. In cosmology, it's very well known for a long time that you can use this same method to calculate the correlation function of dark matter halos, right? Essentially, that's the probability that if I sit on a dark matter halo, as opposed to just a random point in space, and look within a sphere a certain distance away, that I'll find another halo, relative to random. So dark matter halos are correlated, meaning when I say correlated here, or clustered, is what people from cosmology will say, although they don't mean the same thing as you mean when you say a star is in a cluster. It's a statistical statement that says that you're more likely to be near another galaxy than an empty point in space, and that's very true for stars. Whether or not all stars form in clusters or don't, it's very unambiguously clear that at least when stars form, they are statistically correlated. They're clustered in this statistical sense. They're more likely to be near other stars. And so you can make a calculation for that. You basically say, if I'm inside the same parent region, what are the probabilities that two subregions within the same parent region or within the same sphere of a given size will either both have stars or both have cores or both not have cores? And you get some prediction, which is shown here, for the amplitude of that statistical correlation function as a function of separation. And all these different curves are just different variations in the model. The important thing is that you get something with a very large absolute value on small scales. Physically, that just means that this clustering strength is very high. You're very likely to be near other stars when you form, or cores are very likely to be near other cores. And the reason for that is very simple. It's mathematically shown here. This is just the variance in the density scales as this log of Mach number squared. But physically, the way to think of it is, again, turbulence drives the density fluctuations. Most of the power in turbulence is on large scales. So you're unlikely to be in a low density region on large scales, in say a bubble in the Milky Way of very low densities, and have some random tiny scale shock on small scales suddenly jump you up to core densities. That's pretty unlikely, if not impossible, for mass conservation reasons. What's much more likely is that you'll be in a very dense molecular cloud, you and many other potential star-forming sites, and the stars will form in the small subregions inside that cloud that just need to be a little bit higher density still than the cloud itself to collapse and form cores. And that's where most of the stars will form. So that's a fairly natural consequence of this. And again, you can compare this to observations. It's very encouraging at the order of magnitude level, but I really want to stress for you at the order of magnitude level. There's a lot of dynamic range on this plot. So the black curves are the different model predictions for different parameters, and these are different observational estimates of the clustering of stars. There's actually very interesting physical differences between these different model curves, and they differ by a factor of 5 in these predictions. The observations do 2, so it's a little hard to pick one out and say definitively it's the best model. But I think there's information here to be gained beyond just what I've done here, which is the absolute crudest thing, and thrown 5 models against 10 observations. So there's a lot of interesting things to still think about. So before I go any further, I just want to give you a little more context. So what I've presented really builds on a lot of work for a long time in this area. And it's, I think, helps guide your intuition thinking about this to know sort of at least a little bit of the history. And I'm not going to do any level of justice to the real history of this field. I just want to very briefly mention some of the buildup and how this is related to some of the models that people are talking about today, basically from different groups, but really many of them within the same spirit and making many of the same points and really built on each other. So many of these ideas go back quite a ways to people pointing out, I have a couple references here, Larsen and Elmgreen, but there were many others, that this very simple piece of physical intuition, that turbulence and gravity are inherently scale-free, should lead naturally to scale-free statistics in the ISM in many properties. People pointed out that in the extreme limit, if everything were perfectly scale-free, the ISM, certain properties should be fractal, basically, completely self-similar. And that's not exactly what we've calculated here, but it's the same. At a fundamental level, it's really the same concept. So people pointed this out both for large scales, giant molecular clouds, and small. And then Padwin and Nordland made some of the first attempts at using this specific idea that I've built up to make some predictions for the core mass function. And they basically said, let's assume the density PDF is log normal, and then they didn't go through this whole detailed exercise of counting fluctuations on different scales. They just made some very simple assumptions about the sizes of regions of a given density based on, say, okay, here's the characteristic size of a shock, and if that's what dominates these fluctuations, that's what its size will be. And that already gets you fairly well into the ballpark of the estimates we've been talking about. Again, because these are reasonably scale-free processes, they're not as sensitive to those details, the assumption. But you can go to much higher order and add more detail. So Patrick Hennebel and a series of papers has sort of added layers to this and done much of what I've described, where they essentially use this Press-Schechter formulation to more rigorously talk about what the sizes of these regions are. And construct a mass function from it. Now, they assumed that you were inside an arbitrary molecular cloud, just some spherical cloud that had essentially arbitrary parameters, and then they attempted to calculate, given the cloud parameters, what would be the properties of, say, the CMF. And so essentially the model I've described that goes all the way from the galaxy scale down is really just a generalization of that. If I just restrict to the right range of scales, I essentially recover this calculation. So, you know, if people talk about these, don't think that we're talking about actually fundamentally different ideas or approaches here. There are some very different ideas that I don't have time to cover here, but these are all very much in the same vein. And the approach I've described basically just gives you another layer to that. It goes up to the galactic scale and allows you to split between, you know, the biggest objects and the smallest. So you can essentially, you know, take, so this dotted line is what using the formulas in that Hennebel and Chabrier paper would give you. They get the right sort of sum mass function of self-gravitating structures, and what I've described essentially gives you a way to split that into which ones are, you know, parent scales and subscales. What would we define as a core versus a GMC in the observational analog? So, of course, ultimately you want to build up to the next level, well, or some number of levels on, which is full numerical simulations. You can't, you know, ultimately solve the exact system, even the limited exact system with the limited physics we're considering without going to full simulations, which are messy and nonlinear. And you can do all sorts of comparisons of these analytic models to simulations. I don't want to get into this, but this is a lot of what the theme of this summer school is about. And I think the utility, a lot of the utility of these analytic models, there's two, I see, major aspects to them. One is, of course, they give you a way to extrapolate beyond what you can simulate, since you cannot hope to simulate the complete parameter space that real galaxies occupy. It's just too expensive. So you can interpolate with simulations. But that's sort of a crude way to, or with an analytic model, but that's a crude way to think of these analytic models, right? They're not just fitting functions. They should hopefully help us get some physical insight into why things like the simulations, and then of course ultimately the actual observations, why reality behaves the way it does. But it's really helpful to get some insight, I think, because I say this as a simulator myself. It's very easy to run, you know, big simulations that include lots of physics. They do something and you have no idea why they did it. And this happens all the time. And you don't want to ever publish a paper with no idea why it happened. You wouldn't say that, of course, but it happens. Because, you know, not only do you just inherently want to know, but, you know, if you don't understand why it's happening, you're never sure that it's, you know, real versus a bug in the code, or something more evil lurking inside. So that's basically the main sort of background I wanted to talk about. And in the time I have left, I wanted to basically just quickly mention, or let's see, yeah, all right, I'm okay on time. I wanted to mention a couple of applications that I think are interesting and extend this. So for example, as well as some cautions before I finish. So one of the things that this is handy for in the extrapolation sense is you can use these models and this intuition to try and make some guesses about how IMFs might vary within our galaxy and from galaxy to galaxy. So what can we say about that? Well, you know, historically, most theories and most of the fitting functions and analytic models we've had predicted the IMF locally as a function of, say, local molecular cloud properties, which is still, you know, a pretty important thing to have. But it's a little tricky when you want to extrapolate that to galaxies and say, what's the IMF going to look like in the LMC or the SMC, or let alone some high redshift galaxy that we have relatively limited information on. But there have been many, you know, valiant attempts to do this, valiant/foolhardy, depending on your philosophy. And most of them are predicated on the idea that, well, to lowest order, the IMF is all about the gene's mass. And I'm going to argue that's wrong in a slide, but the idea is, okay, what's the gene's mass? The gene's mass is the characteristic self-gravitating mass. However, in a smooth, non-turbulent medium with a single density, a single sound speed. And that, we know, is not actually a good approximation to real galaxies. And I'll show why that can lead to some weirdness in a minute. So many papers, one example I give is from Dave et al. Attempt to extrapolate that to galaxies and say, knowing what I know about the galaxy, how would the gene's mass be different? And you can do different experiments. You can essentially say that means that the characteristic mass of stars will scale as some power of temperature, which is pretty steep. The Jeans mass is a fairly steep power of temperature. So it's something like temperature squared is the characteristic mass. So if galaxies are hotter, they'll have bigger stars, more top-heavy IMFs. There has been much literature written about whether or not the temperature of the CMB alone can cause dramatic changes in this. The answer from everybody I am aware of who's done the calculation in detail is no, it doesn't. The CMB is not the dominant temperature. Essentially at any redshift inside of the galaxies we're talking about, of the star-forming regions that you're interested in potentially having different IMFs. There's a lot more going on from there's local stellar radiation field, cosmic rays, et cetera. So I just want to, at the risk of potentially starting an argument with anyone, I want to make that point. But there are differences in galaxies in the temperature of the gas that arise, as I said, from things like the local star formation. So you look at high redshift galaxies where there's very high star formation rates or starbursts in the local universe. There's a lot of heating going on. There's a lot of cosmic rays being generated in supernovae explosions. There's a lot of photons heating the gas. They're also, at high redshift, lower metallicity, so cooling is less efficient. So it's very plausible that the ISM temperatures are elevated in the dense regions. And you can do various exercises to calculate what this means. So one recent paper from Narayanan et al. Essentially just used this simple temperature. It's very simple estimates of what the temperature in the dense gas would do under these starburst circumstances, coupled to this Jeans mass assumption to predict the mass in the IMF. And this is just an example. This is essentially the turnover mass in the IMF as a function of cosmological time. So this is today. And these are just different models. So the important thing is they generically predict that at high redshift, this is higher than it is today. Basically, they predict that this high temperature means you form more massive stars. So is that actually right? Well, the problem is everything I've said up to now about, at least what these turbulent fragmentation models predict, the turnover that I described was at this sonic scale. Not the Jeans scale, which is what everybody doing galaxy formation talks about. And they're not the same. So what's the Jeans length? Remember, it's in a smooth medium. You can define this. The Jeans length and mass, basically here's the sound speed, the density. So this is the characteristic length of collapsing objects, and this is the characteristic mass. So it scales as sound speed cubed, so temperature to the 3/2 divided by square root of density. What about this sonic scale where turbulence no longer dominates compared to thermal pressure? Well, that scales differently. The sonic length, by definition, is just the length where inside of a sphere of that size, the RMS Mach numbers are 1 or smaller. Okay? You can work out for a disk what that is, and it's basically, in a galactic disk, it's the scale height of the disk divided by the Mach number of the global disk squared. Okay? That's just assuming it's a power law, basically. And then you can work out what this sonic mass is. And by sonic mass, I mean the mass of a minimum mass of a self-gravitating object of a size equal to that sonic scale. And you get this expression, which you can turn into some other expression here. But the important thing is it scales dimensionally differently from the Jeans mass. It depends on, say, the surface density of the disk and its two-way parameter. You could put this is just trying to replace the Mach number with other parameters, but basically it's the same thing. And what this means is that when you run a calculation that I've described, you get very different dependencies than you might otherwise expect. So if I sample, for example, different clouds, the way I've described, and I just say Mach clouds with arbitrary properties, and say what should the CMF or IMF look like inside them. So here's a bunch of different clouds of different sizes and densities. The Jeans mass is different in all of these clouds. But I don't get a very different prediction for the IMF because the sonic mass differs by much less if they're all part of the same turbulent cascade, which is a big if. And you can plug in sort of the equation is just running through the dimensional parameters that I already described. They're not really the important thing. You can run through typical parameters that you might expect for nearby typical galactic disks and say, what do they predict? And here's what they predict. Basically, very little variation at high masses, about the same turnover mass. There are pretty significant gaps that open up at very low masses. But I'll add a caveat about that in just a second. I wouldn't read too much into this just at the moment, but remember it. So you actually don't get much dependence on the gene's mass, which is quite different in these. And this also explains why some simulation results don't get very different answers, even though they initialize clouds in different ways. So I'm just sort of laundry listing some things that don't change the IMF very much. How you set up your clouds in certain ways. How exactly you drive your turbulence doesn't make too much of a difference for the same actual amplitude of turbulence. And things like metallicity, although I'll skip that because I think that's a little more controversial, to be honest. But there are cases where you do expect this sonic length to be very different. And I picked one extreme example. So what about the center of a big starburst galaxy in the nearby universe? Well, in the Milky Way, we know what the gas temperature in the very cold, dense gas is. And we know what the velocity dispersion of that gas is. And that's about what gives the sort of Toomre Q of 1. It's basically marginal stability, but that's not as important here. We basically know what the temperature and the velocity dispersion of the gas are. And we can compare that to the center of a giant starburst galaxy. And what's different there is that the temperatures of the cold gas, while still uncertain, seem to be much higher. From all the metrics that we can get, it seems like they're substantially higher temperatures. So that would naively already lead you to believe they must have very top-heavy IMFs, because the gene's mass goes as this squared. But they also have very large velocity dispersions in the cold gas. 100 kilometers a second is not uncommon as the velocity dispersion of cold gas at the center of one of these starburst systems. So what does that mean? When you plug them in, this is what you'd get as the prediction for those simple parameter choices and everything else being fixed. Here's the Milky Way values, and these dotted lines I compare are the Chabrier and Krupa IMFs shifted by their canonical sort of factor of 3 fudge factor. And the top line is what I get when I plug in those Euler parameters. The hotter temperature has not made the characteristic masses bigger. In fact, the characteristic masses are smaller. So what happened? Well, the gene's mass is bigger, but the sonic mass is smaller, because the sonic mass depends on the Mach number to a strong power. And since these things have such an enormous velocity dispersion, the Mach number is very large. The Mach number can be 100 in these systems. So it's at least conceivable that you can actually get not just quantitatively different, but qualitatively opposite predictions for how the IMF would evolve based on these kinds of differences. And I'm not going to attempt to claim that this is the answer that you really should believe, but highlight how different these can be. It's really what I want to do. And you can confirm that in simulations as well, that at least under idealized conditions, as you increase the Mach number, you get this more and more bottom-heavy behavior. And essentially all that's happening is, as I crank up the Mach number, right, I'm able to generate bigger and bigger density fluctuations and do it on smaller and smaller scales. Right? That's what I said wipes out structure on small scales, is thermal pressure winning. As I crank up the turbulent velocity dispersions, I crank down the scale where thermal pressure wins. And it's just, as I crank up the temperature, of course, the effect goes the opposite way. So you have to actually work through which one wins in detail. So it's very exciting that we can do these kinds of things, but if I haven't already given enough caveats, I want to particularly emphasize that before you get too confident that you can run with these kinds of models, there's a couple of major unanswered questions that they leave open or that I've glossed over. So one major one is, where does fragmentation stop? I said it stops at the sonic scale. But what the heck sets the sonic scale? The sound speed is a number that I just pull out of a hat and say, for this galaxy it's this, for this galaxy it's this, and I plug it into my equations. And it works, but I don't have a reason for choosing the number I chose, let alone what the gas equation of state is. And we also have to ask how we get from cores to stars. So here's the core mass function, here's the initial mass function, and there's that notorious factor of 3 or a few that lurks between the two. So there's physics missing here that we're glossing over. So one thing that surely happens is that these stars blow out some of the mass around them. You've got outflows from the stars, and these winds can blow away material. So maybe we can just multiply the core mass function by 0.3 and say they blow away 2/3 of the material. That would be nice, and that's what most people, myself included, do. It's wrong. There's almost certainly more complicated things happening, and you see that when you just do simulations where you include, no other physics but what I've described and just this multiplication. You actually don't get the right answer. And one of the reasons for that is because the equation of state of the gas, its behavior as it gets to very high densities, matters a lot. So this is from two different models, the model I described in the Hennebrell-Chabrier version, but it's essentially the same thing. What's plotted is the mass function as a function of gamma, the equation of state index, right? So pressure goes as density to the gamma. If it's isothermal, gamma is 1. If it can continue cooling as it gets denser, if things got denser and denser under otherwise equal conditions, the cooling rate normally goes up. So in fact, you cool more efficiently, which means gamma is less than 1. You have a very soft equation of state. And that means that as you compress things, they get colder, the sound speed goes down, turbulence becomes relatively more important, they fragment more easily. So you get this booming number of small objects. On the other hand, if you invoke a very stiff equation of state, you say as I compress the gas, something happens inside of it that makes it heat up a whole bunch. And then the thermal pressure is much larger, the sound speed gets bigger than the turbulent velocities quickly and shuts down this process, then I can get this very sharp cutoff. And in these models, this gamma is essentially an arbitrary parameter, and it has a huge effect here. So physically, that is determined by a lot of things, and this is where I think we really need the simulations, because we don't have anything like an a priori model for this. And a lot of the models we have are really based on interpolating what other people have done in the simulations. So for example, one of the things that almost certainly is important for setting what that effective equation of state is radiative feedback from stars. These are two simulations by Beatty et al. That show the same region without on the left and with on the right the effects of radiation transfer in the simulations. What you can see is without radiation transfer, things could keep cooling, and you actually can just see by eye how the region continued to fragment into smaller and smaller things. And quantitatively, if you compare that to what's observed, this is just the integrated fraction of mass in objects of a given size with no radiative transfer. This is the prediction, and this black line is what's observed. Basically, they're predicting too many small objects, too many brown dwarfs. And Stella and others have worked on this as well quite a bit and shown that really getting in the ballpark of the right answer really requires that you include these radiative effects. And that has a very, this is not as simple as replacing a gamma in an equation of state. It's a very nonlinear effect, right? The gas gets sufficiently dense, some part of it forms a star. That star then has a very complicated effect on the thermal structure of the medium by way of its radiative feedback. And we can put in very toy model approximations analytically, but honestly, this is where you really need simulations, I think, to make any progress at all. And then, of course, even if we think we've convinced ourselves of an answer to that, which I don't think we have, there's other questions that are unresolved too. What maintains the turbulence? So cooling is efficient on large scales in a galaxy. We've just assumed that turbulence is always there, but turbulence doesn't sustain itself when it's supersonic. It dissipates on basically a crossing time, a dynamical time. So something is continuously pumping up turbulence in galaxies. And we also have to ask the question, why doesn't everything collapse? If everything's just turbulence and gravity, as I described, there's only one direction things go. They all go down. They eventually all collapse. Even if that collapse is slow, even if instantaneously only some fraction collapse, I just wait another dynamical time, and then the turbulence has, reordered things, and now another fraction collapse. And in no time I've collapsed my entire galaxy into either stars or dense nuggets that are self-gravitating. And basically, there's no way to stop that from turbulence alone. Turbulence cannot arrest its own gravitational collapse once it's self-gravitating. So I think, again, the answer to both of these is feedback. Simulations are pushing on trying to include all these messy physics of how stars punch back on the medium around them to try and get the right answer. I could give a whole talk on this, and in fact I have multiple talks on just this aspect, question 2 or question 3 of this. But the truth is it's really an area that we've only just started to explore, I'd say, in detail or at scales that can map between these questions. So I think the answer is feedback, but there's a lot that remains to be seen. That actually was that actually was where I was going to end. I'm normally not that good on time. So anyway, so that's what I wanted to say. I threw these couple notes in case people were interested in talking to me later about things like planet formation or things like how non-log normal, non-Gaussian statistics in turbulence might change this story. It's a very interesting conversation to have, but kind of an aside. So basically, these are the main points I wanted to make about turbulence and gravity shaping a lot of what we see in the ISM and a remarkable amount of the statistics following from this very simple couple pieces of physics. But at the same time, I hope you remember the caveats that particularly where feedback comes in to sustain this cycle and make it really self-regulated is where we don't have a complete understanding yet. So thank you.
You mentioned this at the end of the talk a bit, but I'm curious if you thought about a way to, so the experimental formula model sort of assume that there's turbulence.
Yeah.
But have you thought about a way to include the detail of rebalance the ISM so that you can actually somehow start making feedback or whatever into the analytic?
I've thought about it. The honest truth is I haven't made much progress. Partly because I haven't had a lot of time, but also I think as you know, and you've thought about it, it's a complicated problem. I think there are definitely improvements you could make to the current models, right? You could include the fact that absent feedback, the turbulence is going to dissipate, and we actually know it's not that hard to add a model for how non-driven turbulence, so assuming that we ignore the stars, it's not that hard to account for the fact that the turbulence will decay with time, and then include that dynamically in a model like this. Then you have to make the big leap and say, when I decide that a core has collapsed, how do I pump energy or feedback back into the medium? And that's where the really big uncertainties are. I think there's progress to be made, and you have to link it to the numerical simulations because it's so nonlinear and we really don't have a predictive analytic theory for how that would work right now. But I think there's a lot of progress to be made by trying to tie that to what people are simulating.
All right, if there's no